You're tuned in to the Dish TV, the talk show from SRI International that highlights our people, products, and technology portfolio. This series will focus on the Quantum Economic Development Consortium, or QEDC, supported by the National Institute of Standards and Technology and managed by SRI International. The QEDC is a consortium of stakeholders that aims to enable and grow the U.S. quantum industry. I'm Renita Malhotra Hora, Head of Marketing and Communications. In this episode, my guest is Joe Braz, Vice President of SRI's Advanced Technology and Systems Division and Executive Director of the QEDC. I asked Joe for a little background on quantum science and how SRI was selected by the U.S. government to lead the QEDC.
Quantum information science really is a fusion of two of the most powerful forces in scientific discovery in the 20th century. It's quantum science fused together with computer science. And it's that convergence of information science and quantum physics that makes quantum information science so powerful. Simply put, it offers new ways of gathering, processing, and disseminating information that can provide considerable advantage over classical computation and classical ways of doing these things.
So when we talk about Quantum 1.0, firstly, I should ask, is that the stage where we're at, Quantum 1.0?
No, we're both at Quantum 1.0 and 2.0. Quantum 1.0 is really the notion that you take advantage of the quantum properties of materials the way they're actually found in nature. For example, the band gap in a semiconductor led to the practical implementation of a transistor. But those band gaps are things that are found in nature. And while we can alter them slightly, in Quantum 2.0, we purposely engineer quantum properties into materials to take advantage of their quantum behavior. And particularly, we're taking advantage of the quantum behavior of superposition and entanglement in order to create qubits.
Talking about the power of these qubits, from what I understand as a very, very lay person, it's the power of these qubits somehow that really makes quantum computing more powerful than regular computing. Is that right?
A qubit is a very useful quantum element, which is a shorthand for quantum bit. The idea behind qubits for computation is that you want to keep them extremely isolated from the environment, but proximal to each other so that the quantum computation process can proceed. These are known as quantum gates. And so they act with each other. Quantum computers are vastly, exponentially more powerful than a regular computer. More computing power allows computers to really solve harder problems. And in fact, problems that cannot be solved by digital computers at all. And I don't want to just focus on the computational aspects of quantum. In addition, we have quantum sensors and quantum communications. Those are really actually some of the first movers where you're seeing a real inroads in the quantum industry.
Switching gears slightly from the science itself to the consortium that is really supporting the development of this science, can you explain to us what exactly QEDC is, the Quantum Economic Development Consortium?
The QEDC is a consortium of 160 stakeholders that are in the quantum information industry here in the United States. It was chartered under the National Quantum Act. And what we're doing with the QEDC is working to create a robust commercial quantum industry and the associated supply chain here in the US. It includes manufacturers, users of components, developers of quantum systems and products that enable quantum technology. And the real purpose of the QEDC is to foster a strong quantum information ecosystem, primarily through the development of those enabling technologies and funding their development so that we have a robust supply chain. In addition, we're also looking at standards and workforce development, as well as those use cases that are driving the quantum industry forward.
SRI International was contracted by the government to lead and manage the QEDC. Can you tell us why?
We've been told by NIST, which is our government sponsor, that really SRI represented a one-stop shop for them in terms of setting up the consortium. They and OSTP in the White House, in response to legislation that was passed in 2018 under the National Quantum Initiative Act, really wanted someone to set a consortium up quickly because the act calls for NIST to set up such an industry consortium. NIST felt that SRI had the right experience, that SRI had the industry understanding and the credibility within the quantum science space and the exact personnel to do the job cost effectively. So we were selected to stand up and run the Quantum Economic Development Consortium.
So can you explain the importance of developing this supply chain and this ecosystem as we are developing the science itself? Why must the two go together hand in hand simultaneously?
So one of the large barriers that's standing in the way of quantum commercialization today is the fact that in a typical quantum research or commercialization project, let's say that's 5 years in duration, 5 years long, the first 3 years are often spent sourcing equipment, sourcing components, customizing those in order to be employable within that quantum system that you're prototyping or developing or doing research on. The number of enabling technologies available is limited, and typically they're not servicing the quantum industry itself, but in fact, they are components designed for some other industry that then have to be adopted. In order to speed the innovation cycle and the commercialization cycle, what we hope to achieve is a robust supply chain of those enabling technologies so that instead of spending 3 years to get an experiment up and running or to develop a quantum prototype, that we could shrink that time down to, say, 3 months. And that would be because the developer, researcher, industrialist could find ready-made out there in the marketplace exact devices fit for use that they need for a quantum program.
In this process of discovery, one can only imagine that what is being discovered are advantages, disadvantages. It leads me to ask sort of what are the barriers, if any, that stand in the way of commercialization?
Really, one of the largest barriers to the innovation speed or the cycle of innovation is a strong supply chain. Having that fit for use equipment that can be purchased and brought right on in to a quantum laboratory, whether it's industrial or research, university or national lab. Researchers spend an inordinate amount of time engineering the components that they purchase in order to make them suitable for the quantum prototype or the experiment that they're developing. And so in a typical 5-year program where you have an average of of 3-year initial setup period for equipment, it means that very highly trained physicists and specialists like AMO physicists, atomic molecular optical physicists, are primarily engaged in that initial period in mechanical engineering. They're making homegrown adjustments or fabricating equipment to make their experiment operate. What I'd like to see, and I think what everyone in the consortium is singularly focused on, is trying to reduce that initial 3-year period down to something like 3 months, if in fact that equipment can be purchased off the shelf and you don't need to, for example, wire your own circuit board for a microwave pulse generator, or blow your own glass vacuum container to contain a qubit. But if that can be purchased, it speeds the rate of innovation dramatically. So really the focus of the QEDC is to look at where those gaps are in enabling technology, and then find the research capability and fund that capability to fill those gaps.